So next up, we have Leo Werneck, who's going to tell us about direct collapse black holes. So please go ahead, Leo.
Okay, so thank you for the invitation. It's always a pleasure to speak at the North American Einstein Toolkit Summer School, and I'm going to be talking about a relatively recent project that we have started in collaboration with Bernard Kelly from University of Maryland and NASA Goddard Space Flight Center. Sarah Gosson at the Hofstra University, John Baker also at NASA Goddard, Zach, my supervisor, and John Wise at Georgia Tech. And we're basically trying to study direct collapse black holes and mainly the gravitational wave signatures from these collapses. And I wanted to start with an overview that I guess is probably something that we have already seen throughout the week, but I figured it's probably useful for those that are coming from that just want a little bit more understanding about what we're going to be doing. So first and foremost, the first question is, what are gravitational waves? Sure, there's ripples in space-time traveling at the speed of light, carrying information, and they're caused by the motion or collapse of massive objects, and they're predicted by general relativity and confirmed. The one of the classic representations is just a visualization like this. Hopefully the GIF is playing for you guys. You just basically, the most common thing that we study in the Einstein Toolkit, I suppose, is the binary of compact objects, and as they in spiral, they lose energy through gravitational waves, and then because of that, their separation shrink, and eventually they merge. But of course, you can also have the collapse of a supermassive star, and like a core collapse supernova, and that will also come with the emission of gravitational waves, and this is the type of thing that we are trying to study here. So how do we detect gravitational waves? You guys have had the pleasure of going to LIGO, and so maybe I'm just repeating myself here, but it's probably no surprise to anyone that there are very tiny effects that we can observe here on Earth from these faraway objects merging, and so it's extremely difficult to detect gravitational waves, basically because the magnitude of the wave is inversely proportional with with r, right? It goes so it basically, the further away it is, the lesser the effect that we feel here, and the typical changes in length here on Earth are of order 10 to the minus 19 meters, and perhaps that's hard. It's a difficult number to even fathom what exactly it means, but the proton radius is basically of order 10 to the minus 16, right? So we're trying to measure changes in length that are of order 1/1000th of the radius of a proton, right? Which is an extremely difficult thing to probe. Of course, we have these specialized laser interferometers that are used to detect these changes, and right now we have a network across the globe. We have two here in the United States, one in Hanford here near Washington, and then one in Livingston, which is the one that some of you guys visited. Then we have Virgo in Italy. We have Kagra in Japan, and we have the recently confirmed, I think, for at least for construction in India as well. LIGO, the LIGO ones are interferometers with 4 kilometers of length, and this is a relevant number for you guys to remember for the next slide, right? For in the future at least. So there were two important detections that I want to mention that I think are the ones that are always mentioned in everyone's minds. First one was the first detection ever, GW 150914, with a binary black holes, and this is a very important and interesting detection that was made possible in part because of numerical relativity simulations, right? The templates were used to fit the observed data, and it just goes to show that the work that we do is of extremely important. It's extremely important for observatories like this. And the other one, which is closer to, at least to my heart, because that's mostly what I work with, the GW 170817, which is a binary neutron star event And as far as I know, that's the first and only BNS detection that we have confirmed to date. So hopefully that would change in the future, but yeah. So there are many sources of gravitational waves, and there's a vast spectrum of frequencies in which these waves are emitted and detected here on Earth. And so it's usually useful to have multiple observatories for these different scales, right? So on the far right end here for higher frequencies of order of a few hertz, then that's the one that you have advanced LIGO, Virgo, and Cagra, and other future detectors here on Earth that are used to detect this type of waves. They have detected a few stellar mass black hole, binary black hole mergers, and one neutron star merger, and some other events involving neutron stars. Then on the other far end of the spectrum, in the frequency of nanohertz, you have the pulsar timing arrays, and I forget the name of that square SK. I forget the name of it. But you have other detectors that are specialized in detecting these type of waves that come from the gravitational wave background from supermassive black hole binaries. And then in between, or at least in the frequency of other millihertz, we have the future space-based observatory LISA, the Laser Interferometer Space Antenna, which is on the works and is scheduled to launch in the middle of 2030s. And then in between those scales, there are other concepts involved, but there's no project being currently actively developed to explore those regions as far as I know. But we're going to focus a little bit more on LISA because this is what the work that they were trying to do focuses on. So what is LISA? So LISA takes basically the same idea as what LIGO and Virgo and Cagra do, but they scale it up significantly and then put the observatory in orbit, basically, right? The interferometer in orbit. So instead of having these arm lengths of 4 kilometers like we have here on Earth, the idea is that you're going to have three spacecraft that are forming an equilateral triangle, like the figure illustrate, and they're going to be, the distance between them, the distance in the arms of the triangle here is going to be 2.5 million kilometers, right? This distance has changed from the inception to now, but I think that now this is the number that they settled on. So again, it's the same idea as the current ground-based observatories, just in a much larger spatial scale. And of course, it's going to be launched on space, and then it's just going to basically orbit Earth as Earth orbits the sun, and it's just going to keep doing this over and over, right? So the main difference here is that this will allow us to target the lower frequencies gravitational waves, right? You can think of it as if the wave speed is the product of the wavelength and the frequency of the wave. And so here, basically, because the arms are so much further apart, they're going to be sensitive to waves of much larger wavelengths. And so that means much lower frequency. So with this type of observatory, we can target much lower frequency, while the ground-based ones typically are higher, like the previous figure. But not only that, the resolution is going to be pretty remarkable, right? It's going to be able to detect, to measure distances with a resolution of 20 picometer over 1,000,000 kilometers, which is I should have gotten a better illustration of what that would mean, right? But this is already like a ridiculous precision. And again, like I said, it's scheduled to launch in the mid 2030s. So what are the types of sources of gravitational waves for LISA? Well, the first one is the merging of supermassive black holes. Then we have this extreme mass ratio in spirals, where you have basically one small black hole merging with a much more massive black hole. Then you can have this galactic white dwarf binaries and all the persistent binary with that have a highly accumulated signal to noise ratio. So there's a vast number of scenarios that we're interested in that LISA would be able to detect. But perhaps one question that that one should pose, and basically it's the one that we are going to focus on, is in the merger of supermassive black holes, it's perhaps interesting to understand how one supermassive black hole would form in the first place, which is what this project is basically focusing on. So the direct collapsed black holes is basically trying to understand what is the origin of these supermassive black holes. So it could be the merger of smaller stellar black holes, for example, or it could be a rapid growth of a black hole just because there's just a lot of matter accreting on it, or it could be you have this massive gas cloud that just collapse, right, and then forms a black hole that is already pretty massive. So it's very important for us to study how these form in order to understand how their population is in the early universe. And because of course, if we understand their formation to a point where we can make predictions, for example, of their waveforms, then in principle, they could also be a significant gravitational wave source for LISA. So not only their merger, but the formation of a single supermassive black hole. But currently, there are only a few numerical waveforms available, and this is already a work that is 15 years old, and they started with crude analytical estimates. And so, how do we propose to study this type of problem, right? So we're trying to do a multi-code approach and a multi-scale approach as well. So the idea is that I'm going to talk about this in reverse direction of the arrow, right? So the arrow here is in the increasing length scale, but I'm going to go in the reverse order because that way I end up in the area that I will be working the most on. So our idea is to start at the large scale, cosmological scales, where you're just going to have the massively gas clouds that eventually accumulate density in particular regions and give origins to supermassive stars that can collapse directly to a black hole. And then from this, we're going to move our down our length scale here into what we call the mesoscale, where now we basically have a supermassive star, and that supermassive star is bound to collapse into a black hole. And then from this mesoscale, we're just going to keep following down until we actually get to general relativity and the strong gravity regime where we actually need general relativity to study this. And so our idea is to derive initial conditions starting from a cosmological level simulation to the other scales instead of simply using a random or idealized configuration. So this will use three codes. So the first one is going to use simulations like the Renaissance simulations, which were conducted with the ENSO code. And these are cosmological level simulations. And then from that, we can use the ENSO simulations whenever we spot a region that has a very large concentration that would produce a supermassive star. We can use that to give initial data to another code. It's called MESA, and MESA is the type of code that is useful for stellar evolutions. It's a 1D code, but I'm going to go into a little bit more detail later. You can still study types of rotating supermassive stars. And then, of course, at some point, as we keep evolving that star, it's going to get to the verge of collapse, and then we can no longer use this code because it is a Newtonian-based code. And it would be at that point that we would transfer that knowledge into the Einstein toolkit and would carry on the collapse using full numerical relativity to analyze the formation of the black hole and extract the gravitational waves from it. So going into a little bit more detail, right? The first code, the ENSO project, it has performed the so-called Renaissance simulations. They were performed in blue waters. And the output is basically these vast regions, at least the output that are useful to us, right? These vast regions that contain enough matter that it's likely that they're going to form a supermassive star. And basically what the code will provide us is profiles of the density, pressure, angular momentum, for example, right? And so these are the types of output that we expect from these codes. So this would be the initial density configuration and then the final density halos that come out of the Renaissance simulations. And from it, we can sorry, was there a question? Okay. And so, and then we can also extract, from this, what are the regions that are more likely to produce the masses, the stars with the masses that we want to study. And so from this code, we're going to extract a certain region that either has already formed a supermassive star or is about to, and then feed that into the second code, which would study the mesoscale, which is MESA. So MESA, like I said, is a 1D stellar evolution code. It supports rotation by introducing what is called a shellular rotation. So basically rotations of shells, and depends on basically the radial component. And so it's a way of introducing rotation in a 1D code. It's not really what we normally do in the Einstein toolkit, but it's still one way of doing it. So you can still perform full stellar evolutions with arbitrary equations of state, and it also supports a variety of nuclear processes to include neutrinos, for example. And it takes as input, right, the bulk information from ENSO, and then it basically output a one-dimensional hydrodynamic profile for example, density and pressure and the internal energy of the fluid as a function of the radius of the star. And from these profiles, we can, in principle, extract an approximate equation of state. So the simulations look very different than the simulations that we're used to seeing in the Einstein toolkit, because again, this is just a one-dimensional code, and you're just basically seeing changes in, for example, temperature as a function of density and so on. So it's mostly going to give us information that really is tied up to the equation of state. And I apologize, I think I copied the wrong thing. This was supposed to have a short animation of this evolving into the profile that it is right now, but I think this is just a static image. So yeah, so these are the precursors to what where I would step in, I would say, right, which is to where I can help the most, which is once MESA has equilibrated into a solution that we want to study, that we think is useful to study the collapse of, then from this, we're going to basically try to approximate what is the equation of state from the profiles that we have, and use the profiles to generate numerical relativity initial data, right? So that leads us to the strong gravity regime. And in the strong gravity regime, we're going to use the Einstein toolkit. And as everyone, I think, has already seen before, right, our goal is to solve then Einstein's equations. And as usual, we have space-time on the left, matter on the right. So the space-time can be solved using one of the many formalisms that we are already using, BSSN, Z4C, CCZ4, for example. And then the matter usually will be GRHD or GRMHD, right, for general relativistic hydrodynamics, with or without magnetic fields. And that means that we're going to have to solve additional equations. We could include neutrinos, for example. We could use advanced equations of state if we want. And then there's this communication between space-time and GRMHD, because once space-time has evolved, it tells GRMHD the metric information so that GRMHD can compute the evolution of the hydrodynamic fields. Once the hydrodynamic fields have been evolved, it computes the energy momentum tensor and give it back to the space-time code so that the space-time code can evolve itself. And then that back and forth just keeps happening, right? And then for reference, if you're a newcomer to the Einstein toolkit and you're not completely familiar with it, normally the space-time would be handled by codes like bicol or bicol vacuum if you're not interested in GRMHD. And there are also codes from the McLachlan arrangement like MLBSSN or MLCCZ4. And then the hydrodynamics would be taken care of with using codes like Illinois GRMHD or GRAO-HD, which Sam talked about a few days ago, or GR Hydro. And so how do we link up all of these codes, right? So this is the overview of what we can do, but how do we do it? So the first task is to translate data between the cosmological and the mesoscale, which means transferring data from the ENSO project to MESA, right? And because the results here are going to be very preliminary, they are still very crude. But the idea is that from ENSO, we can extract this, for example, the density and specific internal energy, specific angular momentum profiles, and basically use those as an inspiration for to create a similar star and evolve it within MESA, right? So basically, so far in the project, this is different from the previous projects that I've talked about before, like the handoff, where we take data from the Einstein toolkit and simply interpolate it into a grid from another code, for example, like HARM, where we really transfer the entire simulation data from one code to the other. And here we are basically using the results from one code to provide data to another without actually transferring data between the two codes, right? But once we have this, then we go into MESA, and then MESA comes the second linking problem, right? Where we now have to transfer code from the mesoscale to the strong gravity scale. And this becomes difficult for a series of reasons, right? And the first one is that being intrinsically Newtonian, we don't readily have access to, for example, a metric from MESA. So whenever we transfer the output, it's fairly straightforward to transfer the hydrodynamic fields like density and pressure, for example, but it's often more difficult to transfer the metric. And so we have plans for on how to do that. But for now, we're basically taking the same approach as we did for transferring data from the cosmological scale to the mesoscale. And we're basically looking at what the equation of state should be and what the mass and the rotation profile for the star should be. And we're basically trying to recreate that data, that initial data, completely independent from MESA, right? So we're just using MESA as a guide for now. So the way we're doing this at the moment is with the RNSID thorn, which was I actually don't remember if it was proposed or written by Sturgiolas and Friedman. It was the method was proposed there. I don't really know who wrote the thorn. But it uses this Komatsu, Iriguchi, Hashisu formalism. But we also have the possibility and have already started looking into the possibility of actually using the Frankfurt Kadath or Fuka thorn, which we currently have one of the lead authors and maintainers of the code, Samuel Tudor, in our research group, and so it's very useful because from my experience at least, we have it's very difficult to work with RNSID. But Fuka, because we have the lead author, they really know how to work with the code, and so it gives us a lot more control of what we can do so far as initial data is concerned. It's also far more modern and uses a more advanced method. And one of the beautiful things as well is that Fuka accepts any rotation law that we provide to it. So in principle, we can create more types of initial data than what RNSID can do. But again, we're still in a phase of just doing the easiest thing for now, or at least the simplest thing we can think of, right? And then some preliminary results for the supermassive star collapse, right? So we're basically starting with a differentially rotating supermassive profile from that previous paper that I mentioned before by Saijo and Hawk. And with this, we're using the Einstein toolkit, combining the RNSID thorn with MLBSSN and Illinois GEM-HD. And these are some of the initial results that we have found, right? So basically, I'm displaying here on the left the lapse for different times, and on the right the density at different times. And so basically what we see is that from the initial profile in purple, which is it's up here, it's hard to see, it's behind that green curve, the lapse just keeps going down and down, which means that so we're starting from a rotating star, but it's just collapsing, right? It's just too massive. And so you can see that by noticing that as time progresses, the lapse is just getting smaller and smaller near the origin, which is just indicating the formation of a singularity. And then by evolving this for a long time, you can see here that the scale stopped at 200 M, but if we evolve it significantly longer, this is the mass of the black hole that formed, right? We already have diagnostics that detect the formation of a black hole, and this scale is in units of millions of solar masses, right? So this is forming a supermassive black hole, basically. And while we don't have all the profiles similar to the profiles in the paper, because the simulation hasn't, the previous paper, because the simulation haven't run far enough yet, we are on the right track to getting to being able to reproduce the earlier results, and then from there move on to more to simulations that are more inspired by the other codes. So I guess I'm much shorter than what I expected. I figured that 1 hour was probably too much, but just to summarize what and to close off with future plans. So direct collapse black holes are relevant to LISA because not only they're part of the supermassive black hole population history, right? They are possible gravitational wave sources. So not only the merger of supermassive black holes, but also their formation could be potentially important sources for LISA. And we have a strategy for developing and investigating the formation of these direct collapse black holes and to extract their gravitational wave signals. And it goes from a cosmological scale inspired simulation from a code that can evolve galaxies into a mesoscale to a code that is specialized in evolving supermassive stars until they are about to collapse. And then we move on to a stronger field code like the Einstein toolkit that is able to do full numerical relativity. We're currently in the stages of regenerating published works as a precursor to the more streamlined idea that we have selected, just to make sure that each part of the code is working the way that everyone expects. And we have several open questions like, can we really capture all the relevant physics when moving between these scales? Because we tend to either lose a lot of information or having to introduce a lot of information, and it's not always obvious. If for example, how sensitive, right, the results are going to be to our transition. And we have plans to ameliorate that. So one of the things that we might do in the future, for example, is to use a code like NeRP elliptic to, once we transfer data from the mesoscale to the strong field, and we have the metric, and we construct a metric from that Newtonian data, most likely that solution will not be fully relaxed yet, meaning that it probably will have constraint violating regions just because the transfer was constructed instead of actually being self-consistent. And so what we could do is use a code like NeRP elliptic, which is an elliptic solver for numerical relativity, to relax that solution so that it becomes more constraint satisfying. So that's something that we can do in the later stages of the project. And I have a few plans that I wanted to share for that are probably coming into fruition this summer, or at least that's the goal. And that's we want to study this type of collapses with neutrino transport. And right now, Illinois GRMHT is in a stage where it supports advanced tabulated equations of state, and it supports neutrino physics via a simple leakage scheme. But we do have plans for writing our own Grail and NeRP-based open source M1 closure radiation transport code. I think that if you watched Jonah's presentation this morning, this is what the 2-moment code that he described would be. And with this new code, there will be an accompanying Einstein Toolkit Thorn. And so this will benefit the Einstein Toolkit community as well. Yeah, and I think that's all I had. Sorry, I went, I think, too fast, but yeah.
Great. Thank you, Leo.
Yeah.
First, are there any questions in the audience? Oh, we have several. Great. Roland, you're closest to me. You can go first.
Okay, so we're doing it. So thanks for the talk. I have a question about the population of stars that you're going to simulate. Do you have an idea what kind of masses one has to expect there, and which age of the universe these collapses would happen?
Yeah, I can tell you that the order of magnitude that we expect to study is of order of millions of solar masses. But generally speaking, we would try to let the ENSO simulations be the, once we detect regions that can form these supermassive stars, then we would just track those regions. That's my understanding at least. Was there more to that question? Sorry, maybe I missed.
No, I just want to get an idea. Millions solar masses, a whole lot.
Yeah. Yeah, go ahead.
Is it possible that James Webb Space Telescope produced data which support your results?
I could not understand that. Sorry.
Is it possible the James Webb Space Telescope
Mm-hmm.
data that will support your results?
That's a good question. I'm not sure. That's a good question.
So my question was related to so I just wanted to get a feel for what the cosmological epoch you're thinking about for transfer.
Yeah. Yeah, I don't know how to answer that. Sorry, but I can try to look more about it, and then I can chat with you later. Assuming that's Peter, I think that's Peter.
Yeah.
Yeah. Okay.
I think the bottom line is these clouds have to be extremely pristine, almost entirely hydrogen. So we're talking very early.
Yeah, very low metallicity. Yeah.
Exactly. Basically zero metallicity.
But still compact enough that you don't actually feel the cosmology expansion.
Yeah. Right. Yeah. Jonah, you had a question.
Yeah, thanks for the nice talk. It's really interesting project. Related to the stars question, there's a lot of uncertainty about the structure of very massive stars. So how do you plan to address that? Is there some plan to parameterize over uncertainty and what these stars might look like? I mean, Mesa, I don't think is particularly trustworthy for a million solar mass star, for example.
Yeah, that's a good question, and that's part of the difficulty that has arose when we started looking into this. And right now, we're looking into this simpler approach of simply using Mesa to inspire some. Basically, as of right now, we've looked at different profiles of stars that Mesa is capable of producing that are, at least as far as I remember, as massive as we could get them. And the only goal there so far was to extract a rough idea of what the rotation profile of the star was and what was the equation of state. And so, but even then, right, the crudest possible, we did, the way we found the equation of state was through a plot of, for example, the logarithm of the pressure versus the logarithm of the density. And we saw that for the regions that we were interested in that tend to be represent the densities inside the star, you basically have a fairly decent approximation by setting the equation of state to be a simple polytrope, meaning that if you plot log p versus log rho, you have a straight line right now. And so far, right, that was all that we did. We have one, so Bernard Kelly is the specialist in constructing the numerical relativity data from the Newtonian data that we have. And beyond that, I know that we have the plan of trying to relax it into a more general relativistic simulation using NURBS elliptic. But the trustworthiness of Mesa data is not something that I understand very much, so I don't think I can comment on that right now.
Yeah, another question.
Could you go back to the slide with the flaps in the fluid.
Yes. Oops.
So it
This
looks like the fluid is symmetric across the thing, and you have a rotating black hole. So is this a symmetric space-time?
I would guess yes, because I think that the rotation here is along the z-axis, right? And for this particular choice. And so you would have some sort of axis symmetry.
So I was kind of wondering how, because in axis symmetry, I think you can't produce gravitational waves. So I was wondering how there even is one in the first place.
Notice the mode. Leo, if you go one slide forward, the mode that you were analyzing was 2-0.
Mm-hmm.
2-0 mode, not the dominant 2-2.
Mm-hmm.
Oh, okay, so you can't produce gravitational radiation.
Yeah, I think it's spherically symmetric can produce, but I think if you, I mean, even with a differentially rotating star, you might not really have axis symmetry, maybe. But I thought we did have axis symmetry
Yeah,
for this.
it's going like this, in rotating along this axis. Yes.
So yeah, I think as far as I remember, there's nothing that prevents an axisymmetric system from producing rotational waves. But spherically symmetric, I think that's true.
Well, we have one online question.
Yeah,
We
that's
have
what I wanted to see. I had a question about that.
Yeah, Leo, could you just check your chat and
Yes.
and if you don't mind, read the question for the in-person audience?
All right. I'm trying to find my chat. Where is?
I can pull it out if you need.
Yeah, I am just gonna have to stop sharing, I suppose.
This is first about the dark matter halo.
Dark matter halo. No, I don't think we have included any dark matter as far as I remember. So the question was, do you include the contribution of dark matter halo? And I don't think
That's not something Mesa would provide for us.
Yeah.
We would have to paint it in, if you will.
Yeah.
It's a good question and quite relevant, one that we should probably discuss.
Mm-hmm.
Roland, you had another question.
Yeah, maybe question and comment. So you start with Mesa and you get perfect radiation symmetry, but initially you put it in the grid. I would expect that you will find some disturbance because volume bonus is 24, but I would think that nature this thing stays radiation symmetric. Do you have any idea if you can have something that's unstable that develops larger asymmetries?
Sorry, I missed the last part. It was cutting a little bit. So when we put the data on the grid, what would happen?
Yes. So the thing is with Mesa, right? You get a spherically symmetric star or massive star in this case.
Right.
The Roland's question, and correct me if I'm wrong, was is it possible that if you were to evolve this in full 3D, that an instability might arise, and that might lead to some more interesting physics?
Mm-hmm. Yeah.
Yeah, like an M1 instability or something like that.
Yeah. Yeah, I mean, it's hard to say. Well, I don't remember if we expect to see any of this, or if this was one of the caveats that we discussed. But there is certainly a worry in what will happen when we try to transition from one code to the other. So this is something that we're definitely going to have to try to be aware of when we start doing the more handoff-like runs. But at the moment, I don't know if I can say much about that.
Yeah, I think the easiest way to put it is, and just reiterating what you said, Leo, there's information that's missing that Mesa doesn't provide that we need. The metric is the most obvious example of that. But also, how do we feed in an axisymmetric system into our numerical relativity simulation from something has cellular angular momentum distributions, which is what MESA provides.
Mhm.
And those are questions that we're going to have to answer. And as far as we're aware, this is the only way one can connect the dots with current codes. It's not like we can start a numerical relativity simulation and evolve it. I don't know if Leo was showing like an example star if you saw it, but it's like, you know, of order of millions of years of simulation in a numerical relativity context is probably not going to be easy. So MESA is really, I think, the way to go at the moment. And we're kind of doing the best we can to fill in the gaps. Peter, you had another question.
Regarding that, I mean, so one of the reasons I think you use MESA for solid boost is because long times with nuclear reactions, but I suspect that nuclear reactions are probably not. So could you maybe use, for example, the Newtonian SPH particle code, collapse things down to a scale where you get close to
Did you hear that, Leo?
So if I understood is in between the MESA and the strong and the Einstein toolkit, we would try to evolve something with like a Newtonian SPH code.
No, I think Peter's idea was
bypassing
just,
MESA completely.
exactly, just completely bypass MESA, go straight to an
Oh, I see.
SPH evolution.
Well, that's a possibility, I guess. And we do have people that we know with expertise on that, but that's yeah.
No,
And we
exactly.
have-
The person who asked the question, yes, of course. No, I mean, this is that's a really great point. I mean, this has a great precedence too in large scale simulations where you want to model subgrid physics, right? This would be subgrid physics for ENSO, our cosmology code. So very good point.
I mean, with the SPH, I mean, let's say very last time steps, while things are still
And you'd have a full 3D initial data for the numerical relativity. I love it. Yeah. It's a very neat idea. Yep.
Yeah, this is definitely something that we can consider as well. Because yeah.
Jonah, you had another question?
Yeah, similar thought. There has been some work for normal stars extracting 3D angular momentum profiles from MESA for the purpose of like evolving the star in 3D down to like pre-collapse. So for example, Sean Couch's group, his former graduate student Carl Fields did a lot of this work. So that might, if you decide to go with the process of extracting an angle-dependent angular momentum distribution from the description in MESA, in a different context than your context, this problem has been solved at least once. So I think there's something in the literature on this. And you can also reach out to Sean or Carl.
Yeah, would it be possible to share the names in the chat at some point? Because I couldn't make out the names, and maybe Zach got it. So
And one of you who is actually in the Zoom call, can you enter those names?
So Carl Fields and who is the other person?
Sean Couch.
Is it Couch is in?
Couch, like the furniture,
Okay.
is at MSU.
Okay.
I think Manas here has all the
yeah, thank you for pointing that out. That's that could be very useful in the future.
Cool. Thank you, Jonah. Duly noted. Cool. Oh yeah, question in the back.
So assuming that we know this will be the band of because of like situation from already done past. But I guess is this just in Lisa's band or like would Lisa be? I'm assuming like based on the initial mass of the star, will it be able to capture the whole range or will it only be sensitive to a certain range of initial star masses?
Yeah, so from our estimates that we're going to target these the particular types of stars that would fall right at the Lisa band. So that this is a project that in principle is trying to contribute information to guide Lisa, right? And so that's our main focus for this one. So it is a Lisa preparatory science project, but that doesn't mean that there can't be other types of or similar types of collapses that would be better suited for other types of detectors, but we're going to be focusing on the ones that are most useful for Lisa.
Peter, yeah.
Just out of curiosity, in your test collapse runs, how many levels of profit?
So it was actually a very interesting problem that I never had to do before. I think to answer your question quickly, I think the maximum is 11, if I'm not mistaken. But it's a very unique scenario from what I have done before, because usually with BNS, we start with a certain number, let's say 7, and then after immersion, when a black hole forms, we add a few more refinement levels, let's say, so that now the maximum is 9. So we added 2 additional levels to support the fact that the black hole is there now. But in this particular scenario, once the black hole forms, yes, it also needs 2 additional refinement levels, generally speaking. But the problem is that there's just so much matter around the black hole that so much accretion happens that the black hole starts to grow again. And then those refinement levels that we added, at least in principle, are no longer needed. And so this was the first simulation that we did that we actually add refinement levels for a while, and then after a while remove it. So yeah, in that case, but I think it's about 11 is the maximum that we have used so far.
Yeah.
Have you looked at BSN, was it C4C, whatever, two other ones? Is there anything that's real equivalent over BSSN?
Sorry, what between BSSN and
Z4C, for example.
Yeah, is there anything that's really an improvement over it?
we're using BSSN. Sorry, I guess I missed the question.
You tried, so you had listed a number of simulation techniques, BSSN.
Right.
Right, so is there anything that's really that much better than that?
Oh, so CCZ4 and Z4C are versions of BSSN or extensions of BSSN that try to make BSSN has a problem where when you evolve it, the constraints are sort of like they have these they can't propagate out, right? So whatever constraint you start with kind of leaves an imprint in the simulation. If you look at constraint violations over of a BNS simulation, for example, you basically have like these little balls of higher constraint violations around the surfaces of the star. And then as the stars move around, if you just plot that in a 2D movie, right? Let's say along the XY plane or the orbital plane, you basically see like those balls moving around in something that looks like honey, right? It's like they drag it around, and there's the constraints just look like they're stuck in place. And the idea of going to C4C or BSSN is to introduce additional auxiliary variables in the equations that basically allow these constraint violations to propagate out. And so in the context of, I think, binary black holes and binary neutron stars, has been shown that in principle you can have better constraint violations or lower constraint violations using those formulations. But that's not the end all be all of the story, right? Zach has published recently other ways of handling the constraint that would damp away constraints that can also be useful. But yeah.
How would you do it, Zach?
I try both ways, see which one works better. May the best technique win.
Pardon?
May the best techniques win.
Okay. But have you found a best technique?
Stay tuned. Stay tuned. We're looking into it. Any other questions? Roland, were there any more in the chat?
No, I think that was it. I'm
Okay.
with that open now.
Cool. All right. Well, wonderful. Well, thanks again, Leo, for the very nice talk. All right, great. Well, I guess
Should we
that,
get